Okay, so now we're going to talk about Laplace transform and the inverse Laplace transform. First, the definition of Laplace transform is given by the following. We have a fancy L given acting on some function f of t, and this transforms it from a time variable to a complex frequency variable given by the following equation. Now, this has many parts to it. One, if we're modeling any kind of physical system where the time function is given by two parts, it really only makes sense. Um, so I would say that it's on when t is greater than or equal to 0, and it is off when t is less than 0. In essence, that when we're modeling some kind of physical system, such as a circuit, a switching circuit, for example, the time function must only really exist for time greater than or equal to 0 or until it turns off. But in this case, we're assuming that once the switch closes, it permanently stays on. So this, although, is formally called the bilateral Laplace transform, but not really useful. So what we instead convert it to is the unilateral Laplace transform, which is simply from 0 to infinity of f of t e to the negative st. So that's one thing. We want to instead convert it to its more useful form with the unilateral Laplace transform. Now, the second thing is that S, as mentioned before, is a complex frequency. In mathematics, we usually just denote it by some A plus BI, but due to us using engineering notation, we instead want to describe it in terms of its real frequency and its radian frequency, or given by sigma plus j omega. This is the real part, and this is the complex part, or the imaginary part. So that is a is the Laplace transform. Now notice a few things. It's an integral. So as such, when we're using an integral, we're asking an area under the curve. And there are a few things to make the Laplace transform, at least the unilateral Laplace transform, converge. Two conditions. So two conditions. One, f of t must be exponential order. Now, what do I mean? Well, exponential order is when your function f of x is bounded by some kind of exponential function given by this relation. So essentially, it cannot be any kind of function which is going to grow faster than an exponential. It has to always be less than an exponential. This gives us a hint as to which Laplace transforms are valid and which ones we can easily say it's not valid. The second condition is dubbed racing. In racing, when we take the limit as time goes to infinity, your time function has to always lose to the exponential function. Or in other words, this has to be 0. So what kind of functions are we really dealing with? So one, we could be dealing with polynomials. Because polynomials grow much slower than exponentials, this has a valid Laplace transform. What about exponentials? Exponentials, yes, only if the complex frequency is greater than a. Otherwise, if it was the case that we combine and the exponential was positive, from 0 to infinity, we get a diverging integral. 3. Sine a bt. Cosine a bt. And actually, these are the main 4. There are a few other ones, such as the step function, the delta function, and subsequently combinations of them. But for now, these are the common 4 that we would care about. And then perhaps later on we'll see what are their Laplace transforms. For now, just to introduce the idea, the Laplace transform acts on a time function to convert it from time domain to complex frequency domain. And the reason why we would want to do this is because maybe solving things in the complex frequency domain is much easier to solve than in the time domain. Think of it like trying to solve a differential equation instead of solving a polynomial. Now, because the Laplace transform is defined by an integral, it is considered linear and therefore has a valid inverse Laplace. Now, I won't go into too much detail as to why this is the definition, simply that this is the definition as given by the Mellon integral. So this is sigma plus j of j infinity plus sigma plus j infinity of f of s e to the st ds. Now, because this integral is rather tedious and, quite frankly, doing this computation is too complicated, we enact the following property. If the Laplace on a time function gives us the complex frequency representation, then by linearity, the inverse Laplace of the complex frequency function gives us the time domain function. And actually, this is a very, very valid property we can state, simply because the Laplace and subsequently the inverse Laplace are inverses to each other and are both linear. Next, we'll explore the common Laplace transforms and why they are common Laplace transforms. Okay, thank you.